The insulating property of a bushing is determined by the material used to create the insulation. This material must exhibit high electrical resistance and a low dielectric constant. Several materials are commonly used for insulating bushings. These include porcelain, epoxy resin, and composite materials. Porcelain is a ceramic material recognized for its excellent electrical insulating capabilities. It boasts a high electrical resistance and a low dielectric constant. Additionally, porcelain demonstrates resistance to moisture and various chemicals, which makes it well suited for applications in outdoor environments. Epoxy resin is a synthetic polymer that also provides exceptional electrical insulating properties. Like porcelain, it features a high electrical resistance and a low dielectric constant. Epoxy resin is resistant to moisture and chemicals, making it appropriate for use in both indoor and outdoor settings. Composite materials involve a combination of different materials such as fiberglass, resin, and paper. These materials provide high electrical resistance and a low dielectric constant. They also offer lightweight properties and resistance to corrosion, making them useful across a broad spectrum of applications. The thickness of the insulation plays a significant role in determining the insulating properties of a bushing. A thicker insulation generally equates to a higher electrical resistance and a lower dielectric constant. However, it's important to recognize that increasing the insulation thickness can also lead to an increase in the overall size and weight of the bushing. Beyond the material and its thickness, the design of the bushing significantly impacts its insulating properties. The shape of the bushing should be designed to minimize the electric field stress that is placed on the insulation. It should also incorporate a smooth surface, which helps to prevent the accumulation of dirt and moisture that can compromise insulation effectiveness. In more detail, high electrical resistance is essential for an insulating material because it minimizes the flow of current through the insulation itself. Ideally, an insulator should prevent any current from flowing, but in reality, all materials have some level of conductivity. A high electrical resistance ensures that the leakage current is minimal, preventing energy loss and reducing the risk of electrical breakdown. The dielectric constant, also known as relative permittivity, measures a material's ability to store electrical energy in an electric field. A low dielectric constant is desirable for insulating materials because it reduces the amount of energy stored in the insulation. This, in turn, minimizes the electric field stress in the material and reduces the likelihood of dielectric breakdown, which can lead to insulation failure. Porcelain is created by firing clay at high temperatures. This process creates a hard, dense, and non-porous material with excellent insulating properties. The high firing temperature ensures that the material is chemically inert and resistant to environmental factors. Its resistance to moisture prevents surface current leakage, while its resistance to chemicals prevents degradation of the insulation over time. Epoxy resin is a thermosetting polymer that is formed by mixing a resin and a hardener. The mixture undergoes a chemical reaction that creates a strong, durable, and electrically insulating material. Epoxy resins can be formulated to have specific properties, such as high thermal conductivity or improved resistance to cracking. This versatility makes them suitable for a wide range of applications. Composite materials combining fiberglass, resin, and paper leverage the strengths of each component. Fiberglass provides mechanical strength and dimensional stability. The resin binds the fibers together and provides electrical insulation, and paper can be used as a filler material to reduce cost and weight. The combination of these materials allows for the creation of insulators with tailored properties. The thickness of the insulation directly affects its ability to withstand electrical stress. A thicker layer of insulation provides a longer path for current to travel through, increasing the overall resistance. However, increasing the thickness also increases the amount of material required, adding to the cost and weight of the bushing. Therefore, the optimal thickness must be carefully calculated to balance performance and cost. The design of the bushing also plays a crucial role in managing electrical stress. Sharp corners and edges can concentrate the electric field, increasing the risk of breakdown. Therefore, bushings are typically designed with smooth, rounded surfaces to distribute the electric field more evenly. Additionally, the placement of conductive parts within the bushing must be carefully considered to minimize stress on the insulation. The surface condition of the bushing is also important. A smooth surface prevents the accumulation of dirt, dust, and moisture, which can create conductive paths and reduce the effectiveness of the insulation. Bushings are often coated with a hydrophobic material to repel water and prevent the formation of a continuous film of moisture on the surface. There are many testing methods which are used to verify the insulating properties of bushings. These tests can be classified into several categories, including dielectric tests, mechanical tests, and thermal tests. Dielectric tests are performed to assess the ability of the insulation to withstand high voltages. These tests typically involve applying a voltage to the bushing and measuring the leakage current. The voltage is gradually increased until either the insulation fails or a predetermined level is reached. Mechanical tests are performed to assess the structural integrity of the bushing. These tests may involve applying a force to the bushing to simulate the stresses that it will experience in service. Thermal tests are performed to assess the ability of the bushing to withstand high temperatures. These tests may involve heating the bushing to a high temperature and measuring its electrical properties. The selection of insulating materials for bushings depends on a variety of factors, including the voltage level, operating temperature, environmental conditions, and costs. For low-voltage applications, inexpensive materials such as paper or plastic may be used. For high-voltage applications, more expensive materials such as porcelain, epoxy resin, or composite materials are required. The operating temperature also affects the choice of materials. Some materials can withstand higher temperatures than others. Environmental conditions, such as humidity and pollution, can also affect the performance of insulating materials. The cost of the materials is also an important consideration. Porcelain is generally the least expensive option, while composite materials are the most expensive. The manufacturing process of an insulated bushing involves several steps. Firstly, the insulating material is molded or cast into the desired shape. Secondly, the conductive parts are embedded in the insulation. Thirdly, the bushing is cured or hardened. Fourthly, the bushing is tested to ensure that it meets the required specifications. Bushings are used in a wide variety of electrical equipment, including transformers, circuit breakers, and switchgear. They provide a safe and reliable way to connect high-voltage conductors to electrical equipment. Without bushings, it would be impossible to safely operate high-voltage electrical systems. Proper maintenance of bushings is essential to ensure their continued performance. This includes regular inspections to check for signs of damage, such as cracks, chips, or surface contamination. Bushings should also be cleaned regularly to remove any accumulated dirt or dust. In some cases, it may be necessary to replace bushings that are damaged or have reached the end of their service life. Insulated bushings must meet a variety of industry standards to ensure safety and performance. These standards specify the minimum requirements for materials, design, and testing. Compliance with these standards is essential for ensuring that bushings are safe and reliable. Failure of a bushing can have serious consequences, including equipment damage, power outages, and even injury or death. Therefore, it is essential to select and maintain bushings carefully. Bushings are a critical component of high-voltage electrical systems. Understanding the factors that contribute to their insulation is essential for ensuring the safe and reliable operation of these systems. From the selection of appropriate materials to careful design and proper maintenance, every aspect of bushing management plays a role in preventing failures and ensuring the continued flow of electricity. There are other types of bushings as well. Oil-filled bushings use oil as an insulating medium. The oil fills the space between the conductor and the bushing housing, providing electrical insulation and cooling. These bushings are commonly used in high-voltage transformers and circuit breakers. Capacitor bushings use a series of capacitors embedded in the insulation to distribute the electric field more evenly. This design allows for smaller and lighter bushings compared to traditional designs. These bushings are used in high-voltage applications where space and weight are critical factors. Gas-filled bushings use a gas such as sulfur hexafluoride or nitrogen as an insulating medium. The gas fills the space between the conductor and the bushing housing, providing electrical insulation. These bushings are commonly used in gas-insulated substations. The choice of bushing type depends on the specific application and the requirements for voltage level, current rating, and environmental conditions. Each type has its advantages and disadvantages, and the selection process must consider these factors to ensure optimal performance and reliability. Advances in materials and manufacturing techniques are continuously improving the performance and reliability of insulated bushings. New materials with higher dielectric strength and improved thermal conductivity are being developed, and new manufacturing processes are enabling the creation of more complex and precise designs. These advances are leading to smaller, lighter, and more efficient bushings that can operate at higher voltages and currents. The development of smart bushings with integrated sensors and monitoring systems is also an area of active research. These smart bushings can provide real-time data on their condition, allowing for predictive maintenance and preventing failures before they occur. The future of insulated bushings is likely to involve greater use of advanced materials, innovative designs, and intelligent monitoring systems. The dielectric strength of an insulating material is its ability to withstand an electric field without breaking down. A higher dielectric strength indicates that the material can withstand a higher voltage before failure occurs. This is a critical property for insulating materials used in bushings, as they must be able to withstand the high voltages present in electrical equipment. The dissipation factor of an insulating material is a measure of the energy lost as heat when the material is subjected to an alternating electric field. A lower dissipation factor indicates that the material is more efficient at storing electrical energy and less energy is lost as heat. This is important for insulating materials used in bushings, as excessive heat can lead to degradation of the insulation and eventual failure. The partial discharge inception voltage is the voltage at which partial discharges begin to occur within the insulation. Partial discharges are small electrical sparks that can occur in voids or defects within the insulation. These discharges can gradually erode the insulation over time, leading to eventual failure. A high partial discharge inception voltage indicates that the insulation is more resistant to partial discharge and will have a longer service life. The aging characteristics of an insulating material refer to how its properties change over time due to factors such as temperature, humidity, and electrical stress. Ideally, an insulating material should maintain its properties over its entire service life. However, in reality, all materials degrade over time. Understanding the aging characteristics of an insulating material is important for predicting its service life and planning for a replacement. The thermal conductivity of an insulating material is its ability to conduct heat. A higher thermal conductivity indicates that the material can dissipate heat more effectively. This is important for insulating materials used in bushings, as they must be able to dissipate the heat generated by the conductor to prevent overheating and degradation of the insulation. The mechanical strength of an insulating material is its ability to withstand mechanical stresses such as tension, compression, and bending. A higher mechanical strength indicates that the material is less likely to crack or break under stress. This is important for insulating materials used in bushings, as they must be able to withstand the mechanical forces exerted on them during installation and operation. The chemical resistance of an insulating material is its ability to withstand exposure to chemicals such as acids, alkalis, and solvents. A higher chemical resistance indicates that the material is less likely to degrade or corrode when exposed to chemicals. This is important for insulating materials used in bushings, as they may be exposed to chemicals during installation or operation. The moisture resistance of an insulating material is its ability to resist the absorption of moisture. Moisture can significantly reduce the electrical insulating properties of a material. A higher moisture resistance indicates that the material is less likely to absorb moisture and will maintain its insulating properties in humid environment. The arc resistance of an insulating material is its ability to resist the formation of an electric arc on its surface. An electric arc is a high-temperature plasma that can cause significant damage to insulating materials. A higher arc resistance indicates that the material is less likely to be damaged by an electric arc. The tracking resistance of an insulating material is its ability to resist the formation of conductive paths on its surface due to the flow of leakage current. Tracking can occur when dirt, dust, or moisture accumulates on the surface of the insulation and provides a path for leakage current to flow. This leakage current can gradually erode the insulation, leading to eventual failure. A higher tracking resistance indicates that the material is less likely to develop conductive paths on its surface.